Right, hello Year 9, this is Mr. Tickner, and this is a video walking you through the parts of the homework booklet that you'll have done ahead of the assessment. And I hope by watching this, it'll give you a good idea of the key ideas we've covered, and if you've got anything wrong, you can sort of see what things are. Okay, so ahead of this, we've done a few of these homeworks. So let's go through them and I'll highlight the important parts. So number one is all about units. Okay, so we had these different units that we're going to deal with, and units in physics are really important. And you might have come up with lots of different weird ones, but these are the only key ones you're ever going to use in physics. So mass, you're either going to measure things in kilograms, which is kg, or grams. Okay, kilograms or grams. And importantly, remember that there are 1,000 grams is equal to 1 kilogram. So if you're ever given a number in grams and you want to turn it into kilograms, you divide by 1,000. Okay, so these are the only two. Weight, there's only one unit you're going to use, which is the Newton, okay, or an N. Length, well, things like meters, centimeters, etc. We don't tend to use miles very much. Volume, well, ones you might come across meters cubed, centimeters cubed, and you might also come across milliliters. Okay, a centimeter cubed is the same as a milliliter, so this tends to be used when you're measuring liquids. Okay. Density, which is not a thing you've met, you have seen the units if you've done the research for it. Density is kilograms per cubic meter, or the other one that tends to be used is grams per cubic centimeter. Area, things like meters squared or centimeters squared are the ones that tend to be used, and pressure. This one tends to be newtons per meter squared, which is sometimes called, also known as as a Pascal. Okay, so a Pascal is 1 Newton per square meter, and the other one tends to be used as newtons per centimeter squared. So these are the only ones that you ever will use as you do your GCSEs from this topic. Okay, so let's go through the homeworks that we did. So for homework 2, weight, mass, and gravity. So with this one, the key equation that is being used here is this one, which is that weight equals mass times gravitational field strength. Okay, so that's an equation. It's the first one we met. It's one you need to keep in your head. Okay, and the real thing is, remember that weight is a force that's pulled down on you. Okay, and weight is a force that acts on masses when they're affected by gravity. Okay, so wherever you go in the universe, your mass doesn't change, but the gravitational field strength from different parts of the universe is different, which means you've got a different weight. Okay, so you will always have mass, but you might have different weights depending on where you are. And so this is a thing here. So which planet is the object with the largest mass? Well, this is recognizing, oh, it's Mars. Fantastic. So that first one, Mars, 6 kilograms. It's the biggest number. How can you tell from the drawings that the gravitational field strength is greater on Earth than on Venus? Well, we've got the same mass, but we have a different weight, and on Earth it's bigger. So, so same mass, but bigger weight. On the Earth. On which planet is the gravitational field strength the largest? Well, that's going to be Jupiter, because we've got the smallest mass, but the biggest weight. On Earth, the gravitational field strength is 10 newtons per kilogram. And that's important. You will get given this number. Okay, you get given it. It's one of the constants that you're kind of given, because most things are happening on the Earth. What is the weight of a 40 kilogram mass child on the Earth? Now, importantly, whenever we put stuff into this equation, you will always get a mark, one for remembering the equation, and the other for putting numbers in before you worry about rearranging. That's true of all equations that you meet in physics. So, okay, so we'll put the numbers in. What is the weight of a 40 kilogram child mass on the Earth? So we have weight is equal to mass, which is 40, times 10, and that's 400 newtons. A car on the Earth has a weight of 8,500 newtons. What is the mass of the car? So we'll put our numbers in here, but this time we've got a weight. So we've got 8,500 is equal to mass, which we don't know, times 10. So something times 10 is 8,500. Well, that's pretty obviously, we can rearrange that. 8,500 over 10 is equal to the mass, and that equals 850 kilograms. There we go. On Mercury, we've got a space probe. We've got a mass of 140 kilograms. We've got a weight of 532 newtons. So what is the strength of gravity on planet Mercury? So we put these in. We've got 532 is equal to a mass of 140 times gravitational field strength. So we've got 532 divided by 140 is equal to the gravitational field strength, and that comes out as being 3.8 or 3.6. Let me just double check because I haven't got it written down. So 532 over 140, 3.8. Yeah, so 3.8 newtons per kilogram. Always remember your units as well; they're quite important. On the moon, the strength of gravity is 1.6 newtons per kilogram. What's the weight of a 250 gram rock? So the key thing we've got to highlight here is that this is in grams. Okay, so the first step we have to do is turn that into kilograms, because that's what we need to make the units balance. So what we need is, so 250 grams, we divide that by 1,000 is equal to 0.25 kilograms. And so we want to use W weight equals 0.25 times 1.6. And that comes to being 0.4 newtons. And there we go, that's what we had there. We've got a probe with a weight of 1,400 newtons. If you forgot to do this first step, you would drop a mark. Okay, so you don't lose everything, but you drop a mark if you don't do it. A probe has a weight of 1,400 newtons on the Earth, travels to the surface of the moon, calculate the mass of the probe on the Earth. So we've got 1,400 as the weight is equal to mass times 10. So therefore the mass equals 140 kilograms. The mass of the probe on the moon, mass is the thing that doesn't change. It's the same amount of stuff, same number of particles over on the moon. So this probe when it's on the moon. So the mass is still 140 kilograms. The weight of the probe on the moon, well, we've got weight is equal to mass, which is 140 times 1.6, which is 224 newtons, I think. Right, okay. So the next big topic that you did was all about stretching materials and things. So there's a lot of practical stuff, stretching springs, stretching elastic bands. Hooke's law is this thing. So a student investigates how the extension of a spring, so key thing here is extension, varies when he hangs different loads from it. Write a plan for the student's investigation. This can be bullet pointed. Often it's very helpful to bullet point things. Now in an extended question like this, there's a 5 marks. You're looking to say 5 things. If you say 5 unique relevant things, you get the marks. Okay. So remember, nothing is so really daft as it. But the way in which these sort of practical questions work is they're not interested in sort of like overly sort of like, you know, descriptive text of things like, oh, first you should go and set up the equipment. You're interested in the following. Okay. You're interested in what you're going to measure, what equipment you want. Okay, to take those measurements, what you're going to do, so how you're going to process the data you collect, whether that's whether it's in a graph or like in an equation or whatever it is. So what you're going to measure, what equipment you need, what you're going to do with your data, and anything that you can add, which is about good technique. So often these will always be about experiments that you will have done or will be very similar to things you have done. So it's just, using your experience, what's good practical technique given this experiment. So, and there tends to be a lot of marks. So what are we going to measure here? Well, we don't measure extension. We've got to measure the length. So the first thing we'd want to do is first thing is measure the original length of the spring. Okay, so measure the original length of the spring. That's the thing we've got to do. The second thing we'd do is we would then add a load. Then we would measure the new length. Okay, and then we can process some. Oh, sorry, I'm not talking about equipment. Sorry, with a ruler. Okay, so that's actually a marking point there. So measure the length with a ruler. That gets you 2 marks out of 5. Add a load or weight or whatever. Mass. Even though it's really, weight is the thing you're trying to like. Measure the new length. Something extension equals new length minus the original. So however you want to phrase it, if you're saying that you take the difference of the lengths or you subtract the original from this, that's how you get the extension. Now I will say, okay, if you said measure the original length of the spring with a ruler, add a weight, measure the new length, calculate extension. You're either on 4 or 5 marks already, and you barely said anything. What would we then do? We would increase the load, okay, and measure again. Okay, so this is kind of definitely getting 5 marks. You may not get a mark for saying measure new length and measure a little, because that's kind of the same thing. You're measuring the length of the spring. Anyway, so that's what we're doing to collect loads of data. So what are we probably going to do with this data? You can plot a graph of load versus extension. Okay, and then we get into what's good technique. Well, I would always go with repeats and average each reading. That's good technique. That's almost always its own bullet point. And something that we could say about this is, I would say, measure at eye level. Okay, so if you're measuring the extent of the spring, so there's your ruler, which is not the best line. Oh, it's turned into a straight line for me. So there's my ruler. Let's see about. Oh, that's exciting. Do a straight line. Oh no, ruined it. So there's my ruler. If I want to measure this accurately, I need to look at eye level. So exactly at eye level. So my eye needs to be there, okay, to get a good reading. If my eye's up, so I would read that sort of there. If my eye is looking sort of downwards and I'm not being very careful, and I look at this, then actually what I'm going to see is I'm going to see a reading down here. I'm going to get the wrong reading. So always look at eye level. There's other things you can say, wait for it not to, wait for it to be still. That's perfectly fine. But those are the things that I would say are key. Right, got a plot. This is our data. Label the axes with a supernal measurement of unit. This is the force or the load, which is in newtons. This is the extension, which is in centimeters. Mark the elastic limit of the spring. It is where it stops being a straight line. Mark the region where Hooke's law applies. It's this bit here. Okay, so this is Hooke's law. Okay, Hooke's law, it's something that comes with the next question, but I'm just going to say it. Hooke's law is that the extension is directly proportional to force. Okay, that's what Hooke's law is. Okay, up until the elastic limit, the spring exhibits. Explain what's meant by the term elastic behavior. Okay, so elastic behavior is 2 marks, 2 things to say, and the first thing is when the force is removed, okay, the spring returns to original shape. Okay, so now this is something to be very clear about, is that being elastic, which is what this means, does not necessarily mean you're following Hooke's law. For a metal spring, whilst you're following Hooke's law, you are also elastic. But you can be an elastic band and you don't follow Hooke's law, but you are. So you don't follow Hooke's law if you're an elastic band, but you are elastic. So for those who've sort of either forgotten, if you have the force thing for an elastic band, it looks like this. Okay, and there isn't a nice sort of like straight region like this. But even once you get up to here, if you let go, it'll go back to its original shape. So that's this homework. Right, number 4, which is again on Hooke's law, a bit of processing of data and so on. So here's the first one. So we've got a student using a digital caliper to measure length of the spring. Spring is bendy and difficult to measure. It takes 6 readings, shown below. What is the average length? Now, this is a bit of practical skills, and it is this thing here, right? So this here, 20.44, sticks out like a sore thumb, because look at this, 3.1, 3.3, 3.0, 3.0, 3.3, 4.4. This is an anomaly, okay? So this is here an anomaly. And if you have a lot of data and you've clearly got an anomaly, this is a reading, because if you're reading the same spring each time, this is wrong because you've done something wrong, and therefore you can ignore that result. So an anomaly is something you can get rid of in your averages if it's something that's obviously wrong. Okay, so it's weighted. There are 5 readings say this and then 1 saying this. So we do ignore that. So when you're working on your average, a normal thing to do on average is to add all these things up and then divide by 6. Okay, so if you do that, you get 1 mark. If you add them all up, divide by 6. To get 2 marks, you've got to recognize you disregard that one. So in there, you would put 20.31 plus 20.33, 20.30, 3, and 3.0. You add all these up, okay, and then you divide, and then you take that number and you divide by 5, because actually we're ignoring that result. And that comes out as being 20.3, I think it's 314 it comes out as being. If you add this anomaly in, you get 1 mark, but you'll end up with something that's inflated a little bit higher. I think, just double check what you get if you do that. So you get, so 3, 1, 3, 3 plus 3, 0 plus 3, 3, 3 plus 6. Yeah, interestingly, you end up if you add it in, you end up with an average of 20.35, which doesn't seem that far away, but that 0.35, okay, if this is your average, that's higher than any of these other readings. It doesn't, so this anomaly actually pulls your average above all of your other 5 results, and so that's why we would ignore it. Okay, then we had a graph plotting one. Okay, so we've got stretching the spring, investigates extension using 6 different weights. The results are shown below. So we want to plot a graph. So we're going to plot a graph of force in newtons against extension in millimeters. And so what do we say? We've got going to go up in normal. So 0, 0.2, 0.4, 0.6, 0.8, 1.0, and 1.2. And then there's 0, 4, 8, 12, 16, 20, 24. Those are our values. Right, I'm going to make this a bit. What are we going to get our values at? So, okay, so we've got that point there. We have 0.4 and 8.4. So 8 point there. We have 0.6, 11.8. So we have that there. 16.2. So 16.2 is there, about. 1 and 20.4. So there. and then we've got 1, 2, and 24. So this is a straight line. So I'm going to do a different coloured pen, do this, and see if I can get this to go in a nice straight line. Excellent. So this is the straight line for this, about here. Yeah, either of these is fine. So I'm going to go with no, it sprung up. So it's a straight line. It doesn't go through all the points. That's not a problem. Okay, it doesn't have to be dot to dot. You get the scatter because they're real pieces of data, and sometimes you don't measure things entirely accurately. So it's a straight line. Okay. Student writes this conclusion: the spring follows Hooke's law. Comment on the student's conclusion. So this question is basically saying, are they right? And if they're right, how do you know? So the first thing, as I'd say, is that I need to say, well, what is Hooke's law? So Hooke's law is that force is directly proportional to extension. Okay, the graph is a straight line through the origin, and if you've got a straight line through the origin, that means that it's directly proportional. Okay, so this is proving that this is true. Okay, so this is backing up this, so therefore the student is correct. Okay, so you can't just get a mark for saying, oh, the student's correct or the student's incorrect, because that's just a 50-50 guess. But so what you're saying is saying here, you're saying, okay, what is Hooke's law? How does the graph, what is the graph doing? Therefore the student's correct. Okay, and that's kind of how you get the marks for that. Okay, so let's go to the next bit. Okay, so right. Okay, so then we have the student extends the investigation by finding information about stretching of wires. So we have describe the stretching of the wire shown by referring to the graph. Okay, so again, key instructions. So make sure you pay attention to instructions. Referring to the graph, that's important. Okay. So what can we say about it? So the initially, we're going to follow Hooke's law. Okay, or we've got initially we've got a straight line, or it's directly proportional, whatever. So that's our initially following Hooke's law. We then enter a region of where we are rapid extension. So we then have a sort of rapid extension where the wire is permanently deformed, and then ultimately the wire breaks at about 16 millimeters. So there's other things you can say if you the thing is, so initially following Hooke's law, we then get rapid extension, because this slightly goes where it's permanently deformed, and you get the wire breaking at just over 16 millimeters. Actually, it's probably about 17 millimeters. The other thing to be saying is how can we refer to the data, and this is your key point here. It's up to 37.5. Okay, so if you say up to 37.5 newtons, okay, that is essential for the thermal. So either about the point at which it's breaking or the point of no return. You can say 37.9, or you can say 4 millimeters. Some reference to this point here is kind of crucial to get the mark, or to this point here in terms of what point on the graph it is. What's the force? What's the extension at this point here? So if they ask you to refer to the graph, make sure you're referring to what that's doing. Okay, and that was our question of Hooke law. Right, okay, then we had pressure, and we've met two types of pressure, solids and liquids. Okay, so pressure from solids using the relationship pressure is force over area, fill in the missing gaps in the table. Okay, so pressure is force divided by area, so force over area. I'm just going to have to quickly race through this one. So 15 over, so it's got this divided by this, 15 over 0.45. So we've got 33, okay, 33.3, but you don't need to write down everything. 3,200 over 12, so 267. 480 divided by 1.6. We've got 300. Okay. Then we've got to work out the force. So if we rearrange it, if we think about putting this in, we've got pressure, force over area. So we end up with pressure times area is force. So we actually are multiplying these two together. So we've got 2.5 times 14. We've got 35. Is this one here? 6 times 0.002. 2 is 0.010, 0.012. 6 times 0.001 is 0.06. And then if we're doing this one, we've got pressure, force, we've got pressure, so we end up wanting area, and we'll end up with actually this one divided by this one, so 8,000 divided by 250, so we get 32. 220,000 divided by 100,000 comes out being 2.2. Oh, excuse me. And again, and 2.5 divided by 0.004. Okay, 625. Okay, so key thing about what pressure is that it's force, it's how squished in a force is. So are you squishing your force into a small area or into a big area? Okay, right, we have a box made from aluminium, has sides of length 2 by 3 by 4, it's got a weight. What's the largest and smallest pressures it can exert on the ground? So let's just quickly, just over here. So here's our box. We've got a 2 centimeter box, line 3 centimeters. We've got 4. Now I've made that optical illusion cube that keeps flipping around. Anyway, so there's, okay, so we've got 2, we've got 3, and then we've got 4. So basically with a cube, you can actually put it on any side you want. Okay, you can put it on this side, which is 2 times 3. So we put it on the 2 times 3 side, which has an area of 6 centimeters squared. We can put it on, let's use red. We can put it on the side it's currently on, which is the 2 by 4 side, which is 8 centimeters squared. Or we can put it on this side here, which is the 3 by 4 side. This is 12 centimeters squared. And given the same object, if you've got the biggest area, okay, that is going to be, as pressure is equal to force over area, this is going to be the smallest pressure, and this one is, because it's the smallest area, this pressure is going to be the largest pressure. Okay, so because if you've got the same weight over in a small area, that's a larger pressure than if you've got it over a big area. So let's go back to this. So our largest pressure is going to be 0.65 over 6, which is 0.108. We're in newtons and simply squared, so newtons per centimeters squared. And then the other one is going to be, go back to my blue coloured pen. I've got 0.65 over 12, which is 0.054 newtons per centimeter squared. Okay, so that's a smaller pressure because small number. This is actually half the size, and this one would be in the middle. Question 3 is something to do with density, and that's because we decided to change how we're doing it, so we just ignore question 3. You can come back to it when you've done density. Liquid pressure, right? Last time worked, we're nearly there. If you've listened to the whole video, well done you. Okay, so we've got demonstrating pressure difference in water. The apparatus is hollow. It's so you should have seen this in the lab. Should have been demonstrated to you. What do you see when you have this? So we've got our first thing. The diagram shows the bath coming out of the top tube. Complete the diagram, show the paths of the other water you expect to see in the other two tubes. Remembering pressure is greatest at the bottom. So what we'll get is a stream of that. And then, I don't know why I've got this one. And then finally this one shoots out like that. Okay, so the idea is that they should all curve. But this bottom one actually goes further because of the way the pressure works. So there's one mark for them having a similar shape, but the second mark is for having them sort of crossover. So this one goes furthest away. Explain the pattern. Explain the pattern of the paths and water the tubes, which is that pressure increases with depth. Okay, so and therefore, because these things all have the same force, the same sort of area, so this has got the same area as this one, as this one, as this one. The force on the water coming out, force is equal to pressure times area. If the pressure has gone up, the area is the same, so that actually means that there's force on water at bottom tube is greatest. Okay, so it's been hit with a bigger force, so it's been shooting out quicker. But realistically, actually, just really talking about pressure increases with depth. The pressure difference due to a liquid can be calculated using this equation. Pressure difference equals density times gravitational field strength times depth. So if you're ever asked to use density, you'll be given the density of this. Density of water is 1,000 kilograms per cubic meter. Gravitational field strength of Earth is 10. Calculate the pressure difference due to the bottom of 2.5 meters of water. So we're just putting things into the equation. So we end up with pressure is equal to density. So we've got 1,000 times 10 times 2.5. So that is 25,000. And our unit here is newtons per square meter or pascals. Either of those units is fine. Pressure difference at the bottom of 75 meters of water. Okay, so the pressure difference is equal to 1,000 density of water times 10 times 75, which is 750,000 pascals. It's an enormous amount. Pressure difference at the bottom of the glass of water that's 15 centimeters tall. 15 centimeters, well, that's only 0.15 meters. So I get there pressure equals 1,000 times 10 times 0.15. So I've got 0.15, 1.5. So that is 1,500 pascals. The height of water needed to create a pressure difference of 5,000 pascals. So this is where we suddenly have to now rearrange this one. What we end up with there is we have height of water needed. So we've got 5,000 is equal to 1,000 density of water times 10 times the height. Okay, so we've got 5,000 divided by 1,000 divided by 10. So we've got, essentially that becomes 5,000 over 10,000. So it's equal to 0.5 meters. So half a meter. The height of water needs to create an additional 100 kilopascals. 100 kilopascals. 100 kilo is 100,000. So we get 100,000 is equal to 1,000 times 10 times the height. If you do all that, you actually end up with h. It's got to equal 10. Right. And final question. The density of Mercury, the element, is this. Density is very high. And on Mercury, the planet, we've got 20 centimeter column of liquid mercury, generates a pressure at the bottom of 9,990 pascals. What's the gravitational field strength on the planet Mercury? Woo, so let's go. So we've got a 9,000, so we've got 9,990 pascals is equal to density, so we've got 13,500 times the gravitational field strength, thing we don't know, times 20 centimeters, so 0.2. So I'm going to take this through in a bit of stages. So what I've got is 13,500 times 0.2 is 2,700. So I've got 9,990 is equal to 2,700 times the gravitational field strength. So divide that through, so 9,990 over 2,700 is 3.7 newtons per kilogram. And there we go. That's how you answer all of the homework questions up to this point ahead of the thing.